we'll start with what exactly we mean by multi-body dynamics. So that is when late a kind of system of bodies and we don't want to see deformations. So this is how it is different from FEA and what we call that. So we are not really worried about how each and every body is being deformed and all. We assume that they are rigid and they are doing some kind of motion, and this is the study of motion. When multi-body dynamics is focused on vehicles or automobiles, that is vehicle dynamics. And this is a very crude definition of it. It might just go on for a while, but I would just stop here. Now I'll talk about so this session is all about motion view and motion solve. That is the multi-body simulation offering by Altair Engineering. So what exactly this is? Basically, motion view is a pre-processor software where you can assemble a model, where you can define points, bodies, you can define joints and connection between it, and then you can submit the job for the simulation, and motion solve, the solver piece of it, takes care of the simulation and gives you the result. So we'll use motion view to build model, motion solve to solve the simulation, and finally we'll use hyperview and hypergraph to analyze the result, and they are our post-processing offerings. All right, so let's start with why we need to even worry about vehicle dynamics. So as in the introduction, that is quite aptly said, that BAJA Student India or BAJA SAE is a competitive motorsport event, and at any event it is just a matter of 0.1%, and vehicle dynamics can make that 0.1% edge, which may help you to get good design points, yes, and also it may affect the dynamic performance of the vehicle and can help you to win or lose that final dynamic event that you are aiming at. Tires, of course, are the most important bit that anybody always talk about. Every vehicle dynamics they always start with tires. Why they are important? Well, if you kind of think this as some kind of event, the vehicle is going to interact with the outside world only on those 4 contact patches of the tires, and hence they are very important. And if you can sap out the full juice out of that contact patch, then that is your race to win. So contact patch is indeed important. So here we have tried to explain in very brief how forces act on a contact patch, how longitudinal forces and lateral forces are there, and the sap of all this is we do want to keep the vehicle always at the limit of the friction circle. Friction circle is a very simple concept. So your vehicle is either sometimes is accelerating in longitudinal direction, or it is accelerating or decelerating in lateral direction. Now if you add up both these components, then you have the total acceleration or the total force acting on the contact patches. Now if this thing this thing has to be smaller than equal to mu g, which is a total available contact patch, mu g multiplied by the normal force would be the total available force, and you cannot exceed that. So once you exceed that, the tire would simply slip, and that means the driver or that means the car has lost its grip and it is out of control. So you always want to be below that. Actually that would always happen. However, just to make sure that you are getting out the complete juice of the contact patch, you at least have to design in a way that your vehicle is always at the limit of this friction circle. That is very difficult job to do, but at least you can design it for that. Right. So now in this So there is one important thing. Wheel alignment is indeed important for getting when we are talking about the contact patch, because now there is also a focus of maximizing this contact patch area, right? And also how the pressure is being distributed in that. And generally you have certain kind of characteristic of tires on which these contact patch force available would be maximum. And you generally want to be, you always want to keep your tires or your wheels at that particular position. And for that, wheel alignment is pretty much important. The important terms that we are going to talk about, the wheel alignment terms, are camber, uh, that is the inclination angle of the wheel in front view. Then there is toe, which is angle of the wheels in top view. And then there is caster. Caster is the angle of the kingpin axis in the side view. Again, why is that important? As I said, the pressure distribution is important. As you see, it has been demonstrated over here for this particular tire. That particular pressure distribution is kind of maximum. If we kind of integrate this area, it would come out to be maximum when this tire is upright. So our design goal, if we want to maximize the contact patch forces, would be to keep this wheel at zero camber position as much as possible. Now the important question is, why exactly these wheel gain any camber angle or any toe or any caster, right? So if you talk about that, we have to introduce a term of instantaneous center. That is, you have these two control arms over here which hold the wheel and which kind of restrict the degrees of freedom of the wheel. And now if you extend these control arms, so this is the front view I'm talking about. If you extend these control arms, they are going to intersect at some position. And this wheel is going to rotate about that instantaneous center. Now assume that you have a situation, you have made this kind of system in which the instantaneous center is at infinity. Now when you brake the vehicle or you accelerate the vehicle, at that point the vehicle is going to experience some kind of pitch. Now while that pitch, the front is, assume we are braking, so front is going to go down. Now when that happens, the wheels are there and the chassis moves down. So wheels with respect to chassis are going to go up. Right? Now because that instantaneous center was at infinity, that means that the camber angle that this wheel is going to gain will be zero always, and we are sure about that. So we have, in this particular scenario, we have perfected our solution, means it can't get any better. However, now assume a different case. In this case, what we are doing is we are cornering, or we say the vehicle is going on a 50-meter radius, and then the vehicle kind of rolls, right? So in that case, if the vehicle rolls, and given this configuration, we know that our wheels are going to gain some kind of camber, like it is demonstrated over here. Now in this situation, the grip won't be enough, right? Or the grip won't be as much as it is possible. So in this situation, we have failed. So although we perfected the solution in one particular scenario when we were pitching, we failed miserably in one situation where we were cornering. Now let's see a case where we perfect the solution in case of cornering. So what we do, we make that instantaneous center exactly here, and so that when the wheel corners or the vehicle kind of gains the roll angle, the camber gain is zero, and that is zero always. So in this situation, that is perfect. So now this solution is perfect However, now let's analyze how this behaves when we are uh, pitching. So we apply brake, and then we again see that now we have failed miserably again. So the bottom line is suspension design is all about trade-offs. If you are going to gain on one thing, you are going to lose on another. So you have to analyze all these concepts wisely, and you have to choose how much in what scenario, uh, how much camber gain you want in cornering, how much camber gain you want while the vehicle is pitching. And if you do that, that's the suspension design. So there is no perfect solution as such, and therefore you need to analyze that a lot, and that's where these MBD simulations come into the picture. Now, is there any doubt up till now? Alright, so let's see now how we are going to do that kind of analysis in the motion view, the preprocessor of for the MBD simulations. So there is 2 or 3 ways that you can do that. I'll choose a way which I am more familiar with, and I can also show the another way which is there for some templates are there which are for BAJA students, and that should make it easier. However, right now I'll just do it like I'm used to doing it. I'll make a half car model of the car. For that I go to model, assembly wizard. In that I select this front end of the vehicle. This won't matter much because we are just focusing on the suspension right now, and we are not worried about drivetrain. Then you can choose all these options. Defaults are fine. Then I choose the type of suspension I want to analyze. I choose front SLA suspension 2-piece. By the way, SLA stands for short long arm suspension. That is the general suspension we use, and mostly I have seen in BAJA. It is not like you have to use that. Then we have rack and pinion steering. Powertrain I'm ignoring. Steering column is fine. You don't need steering boost. Front shocks, I use front shock absorbers with inline joints. Front spring would be front coil spring. Jounce and rebound bumpers you can ignore. Right, so what this does is it kind of opens up a model, a template model, and now, and of course these are parameterized to some kind of points which might not be suitable for you. So you need to update all these points like this pickup points, chassis pickup points as they are on your chassis. The upper ball joint, lower ball joint, tire radius and things like that, right? So where you exactly can do that, you can update all these points, the CG point of the vehicle. You can update all the points over here. So you can choose the XYZ values which are corresponding to your vehicle. So once you do that, you are ready for analysis. Now I'll add an analysis. Say add static ride analysis. In ride analysis, we are going to simulate the pitch scenario about. So in that, we are assuming vehicle is going. So in this, we can choose what kind of suspension is it. Again, we just tell it, and this would be information to the analysis. We can choose static tire radius. What is the vertical spring rate of tire? What is the CG height? Also, you have to input parameters like wheel base. What is the front braking ratio? And you have to enter the vehicle weight. So if you have not calculated any of these parameters, you can start with default values. Right, for running, you need to click on this run button, then you need to choose an XML file. So it is going to write out an XML file which is a deck for solver, and then you run. Now I want to see what is the result of this simulation. For that, and what is good about this approach is this loads all the meaningful results which we need to look at in this kind of simulation. I go to analysis, I go to view report, and there I choose this front right model. Okay, I choose this output. Right, so you can now see that what is the toe angle gain versus the wheel up and down motion. So in x-axis is the toe angle, and what is the ride gain, as in how much the wheel center was moved up and down. So that is for both left wheel and right wheel. So this is for caster. Again, with respect to again the vehicle height gain, sorry, wheel height gain. This for camber. So now your job would be to tweak those parameters in a way that all these things are as you want them to be. So that should be within your design range. Right, so you get all kind of meaningful plots over here and also the animation. So this was the event which we were doing. So you can see that this is a bad suspension. It is gaining a lot of toe when it goes down, so that we call it bump steer, and even that is very undesirable. Why is that? If say your driver is driving on the dirt terrain and you experience some kind of bump in the wheel, if that bump is equal on both the sides, then of course that is going to cancel. However, if that is not so, then your vehicle is going to start turning, and the driver has to counter it, and that is just additional things, right? And that is a bad design. So you need to take care of all these things, and that is where all these softwares come into the picture. Okay. Now let's look at one more analysis like this. So this was ride. Now I want to simulate another scenario which we talked about, which is roll scenario. In this one we simulated when, say we were simulating when we brake the vehicle, how our vehicle is going to behave on that. And now we want to see if we are cornering, what is the camber or the toe that we are gaining in that scenario. So go to analysis again, go to task wizard. Now I want to do static roll analysis. Again, you have to enter similar kind of information, And you see when you put in roll analysis, this ride analysis gets deactivated. You don't really need to delete it. It is already deactivated. There can be only one analysis in the simulation, so the previous one already got deactivated. We go here. Again, I'm going to overwrite the same file. Okay, I'll just put roll in this case. Right, I'll repeat once more that if you need to change the points, you can do that from, you go into this folder and you change the positions of these points over here. The name is quite intuitive, and that would tell you that the UBJ is UBJ, and that is quite globally accepted name. So meanwhile, I'll just check what are all the questions that have been coming up. Okay, there was one question. Hi, so hi. Another question is, can I get a PDF of this tutorial? I think in the package, which is there on the Alta website, which we will share, I think, after this session. There is that PDF. Next is, how can we determine tire stiffness? So tire stiffness is the parameter that you get from the tire manufacturer. So you can simply ask them, drop them an email, and they should be able to answer. If you are using some kind of standard tires, then you might even find that information online. Yeah, okay. So I'm doing some different analysis. I think that would cover the previous part as well. How to import mesh in ANSYS. So I think that would be that is answered in some other webinar. I think the videos are there on the website, and you can see that. I think I found one how to pre-mesh and then import it to ANSYS. You can do that. Where can I get good rims for my vehicle in India? Well, I am off the touch to answer this question right now. Okay, let's see the results now. Go to analysis again, view reports, and I see this front roll, and click OK. That should plot all the meaningful plots for me. Again, we have similar kind of plots. So we have left wheel center Z motion, right wheel center Z motion versus toe gain. And mind you, the analysis right now is the roll analysis. There's a caster that versus the same y-axis, and similarly we have camber. Also, it should tell versus the right. So this is versus roll angle, and this is quite meaningful plot as well. You figure out what is the toe gain versus the roll angle. Similarly, camber. Okay, so we see that the wheel is gaining 5-degree camber as we are rolling from -8 to 8 degrees. That is quite a lot of roll, mind you. Generally, the roll of the vehicle is close to 3 to 4 degrees. Right. Let's see. So this was front suspension. Again, if you want to see the animation, I update the animation over here. And, oops, oh my bad. Test roll dot. Right, so here we see that we are simulating roll scenario over here. Alright, now this was simulation for the front suspension. What is optimum roll angle? Well, that you need to answer while you are designing the vehicle. What is your stiffness of the spring, stiffness of the tire, and that would govern what is the roll angle that you are going to get. And okay, so whatever is the roll angle that you get in the worst case scenario, and the worst case scenario would be the tire limits, right? So you can find what is the roll angle that the vehicle is going to experience, and you pick that roll angle value, you put it over here. Okay, now I would like to demonstrate, I'll open a new session. And right now I'll try to do the similar thing on the rear part of the vehicle. So I choose rear end of the vehicle. Again, I am not worried about the drive line. Choose rear SLA suspension. Coil spring, here I put an inline joint shock absorber. Alright, so this is our rear suspension over here. I add analysis, I'll add the same one, say static ride analysis again. That adds the static ride analysis for rear. Yes. Okay. Yeah, I kind of ignored Johnson rebound. Semi-trailing arm is there, so you can import that. Johnson rebound bumper, I'll just talk about after I finish off this one. Okay, so you again do the similar kind of approach and you'll see what was there for the rear suspension. And just simply jump to the animation part of it, just to show that yes, we did simulate it. So here we have ride analysis for the rear suspension. Alright, so there was one question about jounce and rebound bumpers. So what exactly they are? So in vehicles you have some kind of mechanical stop which restricts the movement of the suspension in case there is lots of suspension travel, and there you put kind of, when you want to restrict the jounce, it is called jounce bumper, and when you want to restrict rebound, you call it rebound bumper. So they kind of restrict the suspension travel. So say you put it after suspension travel of, or I should say wheel travel. Say you put it at a wheel travel of 2 inches, then it would restrict, it would not allow the wheel to go up above that. So that is kind of a mechanical stop over there. But when you are kind of doing this kind of analysis, you can ignore that. Okay, I'll tell you about semi-trailing arm suspension. See that wheel travel according to the suspension. How can we change that's not a 4-link suspension. You do have an option of quad-link suspension. You can choose that for a 4-link suspension. This was SLA suspension. Okay, so I guess this question, how to feed caster camber angle, this is for the initial setup, and that you can do. Think right. Right, that you can do over here. So you can put in the toe and camber. The caster, however, you have to put in the points. You have to update these points, and that should pick up the caster value. But you can indeed put in the static camber and toe, and if that was the question. How can we see that what is the wheel travel according to the constraints? And how can we change camber caster? So camber caster I already told. So what is the wheel travel? You do input it from here when you are putting in the parameters or the initial form that popped up. You can put it there, or if you want to do that afterwards, you can put in any jounce or rebound value. Right. Rollover condition is different. So for that, I guess you have to do some kind of full vehicle analysis, and these half vehicle analysis won't be enough for that. And yes, it is different from body roll, because your body roll might not be much. Body roll is generally defined with respect to tires, and this rollover condition is of the complete vehicle globally. What is difference between wheel rate and ride rate? When your spring rate come into the picture, and when you are thinking about the springs from the suspension pickup point to the ground, and then what is the spring value? In that condition, your wheel rate and also your spring rate are going to couple, and I think they're in series. So in that condition, they change to ride rate. So they are just the terms that you can find at. Which mechanical link doesn't allow it to move? I didn't get this question. Can you just be more in that? All right. So in that condition, I was saying about jounce and rebound bumpers. So suppose you hit a kind, you know that your wheel travel, if it is about 2 inches, in that condition it is going to hit chassis. Your wheel is going to hit chassis. This is generally not the case in Baja car, because they are kind of open wheel kind of vehicles. However, when you have your general vehicle, in that your wheels are covered, you know that the vehicle, if it goes above 2 inches, it is going to hit the chassis, and that is very undesirable kind of feeling. Also, and also for the tires, it is going to just make many things bad. In that condition, it is desirable to put some kind of mechanical stop, and it is a hard rubber that you put in there, and they restrict the movement of the wheel above a particular value. And generally that value should not be hit. But there have been few cases where I have seen that, although it is desirable, I have not seen that much with Baja cars. For all-terrain vehicle, I guess that should be around 5 inches, right? More than 5 inches, I see no reason why the wheel should travel more than 5 up and down. So that is 5" up and 5" down. So that makes it 10 inches of travel in total. I don't think that, I think your axles or something might have maxed out before that. How do I decide air pressure of the tire? Again, your tire specification should tell you that, because tires are made to run on a certain kind of pressure range, and you have to put that. So I cannot say anything about that. So whatever tire you choose, you have to kind of read through the guide or the manual, and that should tell you that. How to insert our respective coordinate with respect to our instantaneous center other than the available. So you can update all these values. However, how to do that with respect to instantaneous center, I really don't know, because instantaneous center is a virtual point. It is not really there. It is just to explain theory or something. So with respect to instantaneous center, can you do that or not? And is it also desirable? I don't see a condition. Which software you are using? Okay, the software is Motion Wave, and that is multi-body dynamics preprocessor of Altair engineering. Tell me the effect of using a negative camber in front tires. What is the difference between roll center and instantaneous center, or is it? No, they are not the same. So instantaneous center, although it is a very generic kind of term, any rotating body you can define an instantaneous center. So instantaneous center is the point about which you can assume pure rotation of the complete body, right? And in terms of wheel, generally we call it instantaneous center. And when we are talking about the chassis, and the point about which it is doing a pure rolling, and that point is called roll center. So they are a little different. How to combine front and rear vehicle to form a full vehicle? Yeah, this is a good question. I was coming to that. I'll skip the rest of the questions. That is fine. So, right. So you already, maybe you have changed some points which are there here. You have changed some points here. You have changed some points in the front vehicle. Now the question is, how do you combine both, and you want to do a full vehicle simulation? So there is a provision of exporting a system after you are done tweaking it. So suppose you are happy with this suspension right now. Now I want to use this in a full vehicle event. So you click on the system, go to import export, go to export, and keep this MDL statement as it is. Choose a folder where you want to do that. So this is rear suspension, and I exported that, and we do similar thing with the front suspension. Okay, we don't really need analysis. We have done that. You just click on this. I go to export again, and suppose I am again happy with this suspension. I finished my analysis with the half vehicle. I want to move to full vehicle now. I do that. Again, I hit on click export. Now make a topology of a vehicle with full vehicle. Right, I choose that full vehicle. Now because we are going to do some kind of dynamic events, we would need some kind of drive line. So I'll say, and generally BAJA vehicles are rear wheel drive, so I'll go with rear wheel drive. Here you can choose, or because we are going to update this anyways, you can leave as it is. You can choose rest of the options. Rear suspension is also fine. I'll choose powertrain to be this one. Don't leave none, because if there is no powertrain, we won't be able to move the vehicle. Okay. And if you indeed have some kind of roll bar and all, you should mention that. So, So we are finished assembling the model. You go to analysis, task wizard, and I'll add some kind of event. Say I'll add this constant radius analysis. Here you can add all kind of data. So I want the vehicle to go on a radius of say 50 meters. And the turn direction I want is left, and the time in circular track. So this is the simulation time, and you can tweak all these parameters. The vehicle control, we want to simulate a 0.5 g acceleration of in the lateral direction. So we are doing that. The entering velocity in miles per hour, we want it to be 35 miles per hour. Maybe we can get it down. Yeah, let's leave it. Okay, because it was too high for BAJA ATV, but it's okay. Now I'll remove these two systems, the suspension, because I want to put one of my own. So I'll deactivate this one, and I'll deactivate the rear suspension as well. So this rear quad link is the 4-link suspension that someone was talking about. And right now I'll go to model, I'll highlight the model, and now I want to import systems into this model, right? So I go to import. There I import the front suspension. Okay, so I just make it something else, underscore modified. Okay, so let's delete last one. That is kind of interfering with the model. Again, I select the model, I want to import the rear suspension. Okay. We do a check model just to see sanity of something went wrong in that, I guess. Okay. I'll just redo the thing. I made something bad. So I deleted both the suspensions. Now I'm again importing them. I'll do this check model to see the sanity of the model, and it passes. Okay, we run the simulation. This might take a while, so I'll answer some questions in the meanwhile. What should be the motion ratio for the front SLA suspension? I would, after this, can you please tell how to import semi-trailing arm suspension? Okay, I'll do that. Do we have semi-trailing arm? Okay, there is something wrong going on. Okay, so that vehicle, I'll choose some different kind of simulation because it is looking like that vehicle is not tuned to do that event. I'll just reduce the velocity because I guess that it might be finding it hard to do that. Was kind of quite hard kind of maneuver. 0.5 G is not less. And so instead of 0.5 G, I'll make it 0.1 G just to make it slightly easier. And the vehicle, fine, make it the same. Okay, so there is, we don't have a defined template of semi-trailing arm suspension in that case. Okay, so I think that we'll put up in our development tickets, and we'll put out when we are ready with that. We don't have a defined template for trailing arm and semi-trailing arm suspension. Right, again, the same thing what it is. Okay, I'll open a model which I know for surely works. And this is what I work on myself, so I know this works. But I think everyone got how to change, how we can delete a system and how we can import a system. Right now I'm going to run a full vehicle analysis with an updated library. And I put here constant radius. So this advanced driver is a new driver that we are trying right now, and I work on that. So maybe I don't know whether that you would find it in student edition or not, but if you do, please do try it. That's a good feature. Okay. So that you can do. I don't want to cover that importing CAD model in this session because that is just graphics, and I really don't focus on that much. Well, creating a small template is, I think, of a bigger session, and we need to do that. It's not a very easy job to create a template for suspension. Of course, you can do that. You have all sorts of joints, points, and bodies. You need to define them properly. And once you do that, you will be able to do it. But however, I don't feel it is a very easy job. So as we see here, the steering angle kind of, so the event that we had was we started on a straight patch of 20 meters. I think it was 15 meters, and after that we started on a constant radius path. Okay, so over here, so vehicle started on straight and then it went into a turn, and because it had some kind of transient response, it was a little wavy response, and after that it kind of got it reached a steady state value. And generally this is what we like to see in full vehicle analysis. What is the transient time? So you generally want to take this as low as possible. So you can comment on this vehicle that it was kind of under steering given the response of the vehicle, because it is very wavy. So these are all other parameters that you can check. So this was the path. The blue one is the path that we wanted it to follow, and red one is what it followed. That is it. And you can also check what is the slip values of the vehicle in the entire event. So these are another things that they are good information at what limit your tire is. So you can keep on increasing the lateral acceleration and you can see how your vehicle is performing. I would quickly run an animation and put tracker on it, make it faster. The video that you might be seeing can be choppy because of this video recording thing, but this is the animation of the simulation that we just did. Okay, so are there any other questions? I'm pretty much done what I wanted to cover in this session. In angle and time graph for which part? So this one was more focused on driver. So in this one, I'm not showing anything related to vehicle. You can find all sorts of signals in a file called PLT. So whenever we run a simulation, there is this file .plt is generated. So if you see for the same name, test underscore full underscore cr.plt. Yeah, here it is. In the user defined, if you go, you find all sorts of signals or outputs that you can plot to see what was the vehicle behavior. In the default template, you might not find everything, right? So you may sometimes also want to plot something else. If we had camber control links in different plane when wheel center in semi-trailing arm suspension, is it necessary to add a toe control link to? No, I guess if you really need to put a particular amount of links, as in to control 5 degrees of freedom, you need to put 5 members. If you don't do that, that means that you are going to put something into bending, and that is very undesirable thing to do. And of course, judges would point that out, and that would that would not be taken well by the judges, I guess, because you should not put anything in bending, especially in case of suspension, because in suspension and when you're designing some kind of all-terrain vehicle, you may get some crazy amount of loads sometimes. In Y component, what are F1, F2s? Okay, F1, F2, F3, so which exact graph you are talking about? Generally, so all this is documented if you go to online help. If you go to help, desktop help, and then there you go to vehicle animation or something, you can find all the simulation, all the information about the PLT. Can we combine road analysis and steering analysis and run? So there is something called KNC event which does exactly what you are trying to do over here. So just run the KNC event and it combines all sorts of analysis. What is the purpose of SDF file? So that tells you all the necessary information about the suspension, so kind of output. It is also output of the result and you can gauge that. Is there any difference if we mount springs to lower or upper wishbone in anti-squat or anti-drag? Of course, there are some differences, but they are generally more of related to which control arm is getting the load and the bending properties of it, and it should not matter much with anti-squat and anti-drag. So ABF and PLT are both kind of result files. The difference between them is one is binary and one is ASCII, so it should not matter to you. They are just, I think only difference is the size difference. So if you want to port it to someone, better port an ABF file because that is smaller in size. All right, so as I mentioned, KNC event kind of sums up all the events. So first it runs right, then it steers, then it does roll. So it is kind of mixture of all the events, and it takes a long time to run. It takes it I think runs for 80 seconds. It runs for. How we calculate lateral acceleration? So you know the radius, that your path radius, and you know the velocity that vehicle is going to follow. So V square by R is the lateral acceleration. Yes, you are going to get a video of this session after this one. So I guess you can access that. I guess we are running out of the time now. So final 4 or 5 questions, if they are, I can answer them quickly. So the angle and time graph was steering angle and time graph in full vehicle analysis. If we kept roll angle 0, then and rolling, what actually will happen? Well, then you are not rolling. You need to give some kind of roll angle in that case. I didn't get this question exactly. So, do you mean that what should be the ground clearance of an BAJA ATV? I don't know. So, ground clearance, generally you have to check what exact events you are going to do. I think ground clearance comes only into the picture in the maneuverability event, where you need to course through locks and all. So you need to check what is in the last event, what was the dimension of all those logs and boulders which are over there. So I was also in one BAJA team, and at that point I think we did good with 12-inch ground clearance. It was fine. We were able to do that. However, I don't know how much it would be this year or how much it was last year. So you need to check it. What is the current status? Is there any relation between length of the vehicle and suspension system? Of course, there is a relation. So your transient response of the vehicle is affected by the polar moment of inertia of the vehicle, which is directly affected by the length of the vehicle. So longer is your vehicle, its polar moment of inertia is more. Of course, its turning radius would be high, and even its because the inertia is high, it would take it it would make it hard for the vehicle to turn as well. Okay, so now please stop with the questions. I'll just answer these ones. We are running out of the time now. Okay, so what should be the rebound travel? As you said, it should be around 5 inch, but 5 inch won't be greater value. Yes, it would be, and generally your rebound bumper should also not engage. So this rebound bumper should come into the picture only in case of some ridiculous kind of suspension travel. So again, so please don't take all these values as because I'm saying that I really would like you guys to design that, and that is what all these competition is about. You can come up with a better value. How can we check with motion that at which velocity our vehicle will be rolled? Well, your vehicle would always roll, and if you are asking me about roll over, right? What simply you can do is you can take this constant radius, you just keep on increasing the velocity. So I guess your tire limit should reach before, or your driver, maybe I should put it that way, your driver who is controlling this vehicle right now, not your driver. So that driver should fail before your vehicle topples over. If that happens, that means that your design is pretty much good and it won't roll over. But that is not a quantifiable thing. You have to quantify that with the tire forces. Okay, so your tire limit should reach. Your tire should totally slip. You might have seen that there was something called longitudinal slip and lateral slip. So that lateral slip value should be 100%, and at that point your vehicle should be on the ground. And if that is there, then you are fine. Well, you can just look at the four-link suspension. So it is there and you can explore that more. And if you indeed have some question, you can ask that at the website that we have that I think you'll get after this session. So that is it. I think now we can stop for today. And there would be more of such sessions, and let us know how you feel about this one. Right, the link is edu-support@india.altair.com, and there you can post all your questions that you have, which I am not able to answer here because of the shortage of time. Guys, it was fun. This was the first time I was doing that, so it was fun.